we are going to do projections now. Okay. So let's define them first. Let V be a vector space. Well, do you know what are idempotent operators? Yes, right. Idempotent matrices you must have seen already, right? So these are just idempotent operators on an inner product space. Okay. All right. Later we will see that this might be slightly generalized. Okay. This the concept. I mean, these are so later we'll see that idempotent operators. I mean projections we could define on spaces, not only which are where an inner product is defined, but where the form is non-degenerate. Okay. Yes. Yes. In a moment, I'm defining it. So this means that P from V to V is, I mean, an operator such that P squared is equal to P. Okay. And you did at least two problems on such a thing. Okay. The first one is that it was diagonalizable, and the second one was that if, well, this equality was not given, but if their ranks are equal, then V is a direct sum of kernel and image of P. Okay. So that, let's give that as an exercise. Okay. So V is a direct sum of kernel P and image P. Okay. And how we get this? At least in this case, this is quite simple. Kernel P is the eigenspace of 0, and this is the eigenspace of eigenvalue 1. And such a thing can have only these two eigenvalues, 0 and 1. Okay. And in particular, if you have V in V, then PV is of course in the image of P, whereas V minus PV is in the kernel of P. Okay. Because apply P over this once more, you get PV minus P squared V, but P squared is equal to P, so PV minus PV is equal to 0. What I'm meaning is that P of V minus PV is equal to PV minus P squared V, which is equal to PV minus PV, which is equal to 0, because P squared was equal to P. Okay. Right. Yes, of course. All right. Now, here's a claim, and actually this claim would lead us to the Gram-Schmidt procedure of orthonormalizing given basis. Okay. So here's a proposition. Okay. If W is a subspace of V with, and V, suppose we start with an inner product space, sorry. Let V be an inner product space, and let W in V be a subspace with orthonormal basis say BW given by W1 dot 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 WR. Okay. So this is exactly the situation you mentioned. Okay, that we are having an orthonormal basis on a subspace. Okay. Then the map, well, let's just write this. Then there exists a unique map P W from V to W such that P W of V is perpendicular to V minus P W V for all V in W. Okay. All right. So we are given an orthonormal basis of W, and with this orthonormal basis will help us define this map P W such that this entire vector space projects onto W, and whatever is left, if you are given a vector and if you subtract from V the projection of V on the on W, this is just PWV, this would be perpendicular to the space W. Okay. Moreover, such a projection will given W such a projection is unique. Such a projection means that suppose we are having some other map P which is a map from V to W such that the image is perpendicular to W. Okay. Yeah, this what I want to say is that not the image, sorry, the image belongs to W, but V minus that image is in W perp. Okay. If such a thing happens, then this is the unique map for which this happens. Okay. In other words, given another orthogonal basis, you will end up with the same map. Okay. Yes. P minus P, yes, of course, it will be the projection of V on W perp. Okay. And this is just a preparatory proposition. That means here we are requiring this orthonormal basis to be explicitly given to us, but we will see that it will suffice actually that V is an inner product space, and we will take any subspace of W that would have such an orthogonal basis with respect to which we can define it. But we should do in between this, because this is a step towards Gram-Schmidt process, whereas Gram-Schmidt process will imply that every subspace of V would have an orthogonal basis. Okay. So basically, this will give us the induction step in Gram-Schmidt process, because we will start with some basis, some subspace, some orthogonal basis. Like for example, if you are given a basis of V, Gram-Schmidt process does what? It transforms the I mean from that basis you get an orthogonal basis, right? So what do? You take the first element and normalize it to 1, okay? And then you can take the span of that as your W, okay? And then project your vector on that, on the span of that. The rest goes to W perp. Okay? And then you actually extend it one by one. So yeah, we'll do it in a moment. Okay. So at first, this map P, let's define it. Okay. Define PW P as, well, as what? This has something to do with the last theorem that we did. Yes? Yes. What we have in hand? We have this basis which we know is orthonormal, and we have an inner product. So the guess is? Yeah? A bit louder? Inner product? Yes. Perfect. Yes. And take the sum. Okay. So summation I running from 1 to R Wi V Wi. Define it in this manner. Okay. So what we must show at first, that it's a projection. Well, at first note that this is an element in W, right? So indeed, this is a map from V to W. Okay. And then what more it should have, for being a projection, what property it should have? P squared should be equal to P, right? So if you apply P once more on this, what will happen? PW V. Okay. That would be just summation I running from 1 to R. Well, actually note that we don't have to compute PW V because it's linear, right? It suffices if we compute it on the basis. Okay. So PW some Wi, small Wi. Let's just compute that. Okay. So at first PW Wi, that would do what? This V would be Wi. I mean some element of the from the basis. So that would be 1, and that would give you just Wi, right? So PW Wi would be PW of Wi, since by definition PW Wi is equal to Wi. Okay. And in particular, for all W in W, this implies that PW of small w is equal to W. That is, W is invariant, not invariant. I mean, PW maps W on itself. Okay. Every vector goes to itself. Or not only it maps capital W on itself, each of it's an identity map on W. Okay. Which one? This part? So we are checking, I mean, what we have to check. So required to check PW squared is equal to PW. That's indeed a projection. Okay. All right. So since it is a, I mean, since this is going to be, sorry, since we must check that this is PW squared is equal to PW, what we should do? We do it instead on the basis, because it's a linear operator. If you have some property verified on the basis, it generalizes to the interspace by linearity. Okay. So we just check it on the basis. Okay. Now note that PW of Wi, what is PW of Wi? Take the definition. Okay. Put Wi there. Okay. Then remember that this is an orthogonal basis. So only the one, the I which is where the indices match, that will survive. Everything else will be killed. Okay. And when the indices are equal, this would just give you 1. Okay. Everything else gives you 0. So for that one, this one would survive. Now which is that? the thing that you put in the argument, okay, this argument instead of v. All right. So only that survives, and that means Pw of Wi is equal to Wi. Should I write it out, or is it clear to all of you? If we can of course write it out explicitly. Do we require? If any of you require, please, Abhinav, do we require this? That is, it will be just 1 minute, but you could also write it down yourself. Just put a particular, say I naught there, okay, and see what happens. Okay. So in particular, since you have Pw Wi is equal to Wi, that would mean for all W in W, you will get that Pw of W is equal to W, because if Wi is being mapped to Wi, any linear combination of Wi's will map to itself, right? So Pw of W, I mean for all, yeah, we have written down for all W in W, this happens. Okay. So that would imply that you have this true, right, for all W in W, right? Okay. Taking what as your projection? This function? Okay, because, well, that was actually the unique choice, right? At first, we saw that any, I mean, given an orthogonal basis, any element in V you can express as this one, where the indices should run from 1 to n, the full dimension. Okay. So now, suppose you are not given a full orthogonal basis, but an orthogonal basis of a subspace. So that means every element in the in that space you could uniquely write it in this manner for V in W. Now let's check what happens with that expression if you take V on the entire space. It will still be an element in W. Okay? And now we are studying properties of that map. Okay? That comes out to be a projection because the image is going into W. Okay? And moreover, I mean, once you land in W, then I mean this Pw, now this, okay, now if you, this is clear for all W in W. Now note that Pw of V, this belongs to W, right? And you already have seen that Pw of W is just giving you W itself. Okay. Exactly. So Pw of V then is giving you just Pw of V, because this belongs to W, right? And we are just applying this one. Okay. So indeed, Pw squared is equal to Pw for all, I mean over or on V. Okay. So this is indeed an idempotent operator on V. Okay. Now we have just defined the map, and that it is a projection from V to W, but we have not shown yet that this is perpendicular. Okay. What we must do for that, we must take the inner product of V with this expansion, right? V, no, not V, V minus Pw V. Okay. So let's compute this Pw V and V minus Pw V. Okay. Can we work this proposition out? Thank you. So I require also a little more space. Is this part also wipeable, or yeah, Bishesh, tell me. Yes, of course. That's That's this component. Because if you add this component with this one, you get V back, right? So the component of V which is not on W in W, you will be given by V minus PWV. That's the rest of the things in V which is not in W. Which one? No, this is just a map from V to W, right? All these Wi's are element of W. So why should we use it here? That V. Okay, let's at first take the picture, and perhaps that would be clearer. Okay, but nevertheless, a picture will help. So this is say W, and your space is V. Okay, and suppose you have some vector V here. Okay, small v. Okay, and then you are projecting it on this. So suppose this is P W V. Okay, and your V minus PWV would be this one, V minus PW V. That P I have not written very nicely. Wait a minute. P minus PW V. Okay. So this is what we are going to. I mean, that is a claim that PWV and V minus PWV, they will be orthogonal to each other. Okay. Let's see whether they are indeed. So here we have summation I running from 1 to R Wi V Wi comma V minus the same thing, right? I running from 1 to R Wi V Wi, right? Note that this will come out to be 0 if we could show that this is orthogonal on each of the Wi's. The picture is like that, right? This is W, and V minus PWV should be perpendicular to the entire space W. Okay. So instead of showing that this is equal to 0, we write that it suffices to prove that Wi and V minus summation I running from 1 to R, this Wi V Wi, this is equal to 0. Okay. If you could show that this vector V minus PWV is perpendicular to the basis vector, that would mean it is perpendicular to the interspace W, and in particular to PWV. Okay. So this one, how do we show this? It's exactly the way we did the last theorem, right? This is an orthogonal basis. So the inner product will kill everything except that I, right? Okay, so this is the same as, so this is the claim for all I in 1 dot 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 R, we have Wi V minus PWV equal to 0. Okay. Proof. Wi comma V minus summation Wj, because we want to distinguish between I and j, I mean the indices, So we change the dummy variable j running from 1 to n, say, and that would give you WIV minus summation j running from 1 to n WJV times WI WJ, right? And note that this will all be 0 except the case when I equal to j. Okay. So this one is equal to WIV, right? Because when I is equal to j, this one is just 1. Okay. That is WIV and this is WIV. So if you subtract one from the other, you just get 0. Okay. So that means this one is perpendicular to every element of the basis vectors. I mean every element of the basis of W. Okay. That is, okay, let's write it here. V minus PWV is in W perp. Okay. All right. Kaushik, any doubt? Yeah, instead of asking Sandeep, you can also ask me. So where is the doubt exactly? Which one? Here? Yeah. The second line from the first line? Okay. So we are taking this inner product, right? And remember that these are just scalars. Okay. So now when you are taking the inner product, remember this is bilinear, right? So this will distribute over this. This is just a linear combination. These are its coefficient is 1. These are having coefficient this. So now when you are taking inner product, this will be WIV minus. Okay. I mean it will distribute over the things. I understand. This is quite natural because I mean when you see this, it's sometimes we forget that these are scalars, and I mean this without the brackets are vectors. Okay. Mahfuz. So till now we proved that this one is perpendicular to this. Okay. All right. Now, by the way, one question. Can you tell me what is this vector? Say you are taking the reflection of V on W, whatever be the subspace. I mean here it is just 2-dimensional, but in general also, can you write it in terms of whatever we have written on the board? PW minus? Exactly, yeah. So this one is called the reflection of, so this is the projection of V, okay. Projection of, well, not only projection, orthogonal projection. Why orthogonal projection? Because I mean this part, whatever it means, belongs to W perp. Okay. So it is basically decomposing V into a space and its orthogonal complement. Okay. Orthogonal projection of V on W. Okay. And then this is reflection of V on W. How do we define it again? Vishesh, you just mentioned. Exactly, because you do this is PWV minus V minus PWV, that's the definition, okay, and that becomes just 2 PWV minus V. Okay. This is called the reflection of V on W, and we can do all this if we have an orthonormal basis of W. Okay. So till now what we have proved, that PW is indeed a projection, and just that, well, V minus PWV belongs to the orthogonal complement of W, these two things. Okay. Now suppose there is some other such map, okay, let P be a map from V to W such that every V in V is equal to PV plus V minus PV, where PV is in W and this is in W perpendicular. Okay. So, in other words, this is giving you a decomposition of W in V in say V1 and V2, and that is giving you a decomposition into V1 dash, call this V1 dash, maybe that will be an easier notation. This is V1 dash, this is V2 dash, this is in W and this is in W part. Okay. Whereas that once what we had already PW, maybe we can wipe this part out. This was the previous part. I mean, wiping it out with just help us represent the things a bit clearly. So, yeah. Now, suppose V has a decomposition in V1 plus V2, where V1 was just PWV and this was what? This was V minus PWV. Okay. One belonging to W and the other belonging to W perp. And suppose you have another map which is giving you another decomposition in this form. Okay. So, what we are going to show is that this map is unique, that is, given V and W, there is a unique orthogonal projection on W, and and therefore a unique component of V on the perpendicular direction of W. So, now this would just give you V is equal to V1 plus V2, which is equal to V1 dash plus V2 dash. Okay. Now, forget about V, just look at this equality, V1 plus V2 is equal to V1 dash plus V2 dash. Okay. Then V1 minus V1 dash is equal to V2 minus V2 dash, right? Okay, yeah, right. V2 dash minus V2. Sure, yes, thank you. Now, where do they belong? V1 minus V1 dash, W, and this one, W perp. Okay. Okay, here you must note one small thing, that W perp is also subspace. Given W, W perp is a subspace. Okay. So, that is why it is closed under this addition or the inverse of it. Okay. And here this one is in then W intersection W perp, because this was in W and this was in W perp. So, it lies in the intersection of them. Now, what is in the intersection of W and W perp? 0, it is an inner product. Okay. In particular, that is non-degenerate. Okay. So, that is 0. Okay. And that implies that V1 and V1 dash and V2 and V2 dash are equal. V1 equal to V1 dash and V2 equal to V2 dash. In other words, this projection is unique. Okay. All right. So, as we mentioned, that is just a middle step towards the Gram-Schmidt process. Okay. We start with one. So, we just did the induction step. Okay. Which board can I clear up? You tell me. The left one, because that was the last board. So, now, okay. Let's stop here then. We stop with the orthogonal projection and what is reflection of V on W, and we begin from here in the next class.